Okay, so this is just a review of our basic algebra and stuff from last semester. The big topic, of course, is the variable. How does the variable behave? We spent quite a bit of time at the beginning of fall semester talking about counts and names. And the fact that that variable, in this case x, but it could be any letter, n, m, y, z, whatever, is just a name. If I have 7 inches, the name there is the inches, the label. Or if I have 7 cows, again, cows is the name or the label. 7x, the x behaves exactly the same way. If I had 3 inches times 5 inches, I get 3 times 5 is 15, but I also have to do inches times inches to give me inches squared. If I have 3x times 5x, the exact same process occurs. 3 times 5 is 15. X times x is x squared. With addition, however, if I had 3 inches plus 5 inches, I get 3 plus 5 is 8. But when I add, I don't combine those names. I don't combine the labels. I just keep the label, inches. 3x plus 5x would be just 8x. That's probably the most common mistake I'll ever see made, is people will try to call that 8x squared. They'll try to combine the x's. But remember, when we add, we just keep the same name. We don't combine them. One of the things this did for us, if you recall, because when we multiply, we're going to combine those names or combine those labels, we could take 4x times 7x. Just going to multiply the counts. 4 times 7 is 28. And then also multiply the names. X times y is xy. Adding, however, 4x plus 7y is going to become, we can't add them because they have different names. When we add, because we keep the same name, it implies that we had to start with that same name. So if we had several different terms, several different algebraic numbers like this, even though they don't all have the same name, we can still go through and combine piece by piece. Which ones here can be combined? 5a and 7a can be combined to make 12a. 5 and 7 make 12, and we keep the same name. Of course, we can also combine 3b and negative 9b. Remember, that minus goes with the term that comes after it. It's not minus a 9b. We treat it as a negative 9b. 3 and negative 9 make negative 6, and it's just a b. A little bit more interesting came when what happens when we multiply. So when we have powers on our variables when we multiply, same pattern, we multiply the counts. 4 times 3 is 12. Now x squared times x to the 5th, what do we get? X to the 7th. Good. If you remember what we got there, x squared is 2 x's being multiplied together. X to the 5th is 5 x's multiplied together. If we multiply all that together, that gives us with 7 x's multiplied together, or x to the 7th. So what are we going to get here? 27 y to the 12th. Good. What are we going to get here? Trick question. That's plus, right? When we add, we have to have exactly the same name. X to the third and x to the fifth are different names. How about here? Can we combine those? Yeah, when we multiply or divide, we can combine pretty much anything. We're going to go ahead and combine the counts. 3 times 11 is 33. How do we do y to the 7th times z squared? That's just y to the 7th times z squared. Would it matter if we did 33z squared y to the 7th? Would that be different? No, it's not. It's the same number. But we talked a little bit about that math grammar last semester, and usually it's most acceptable to put the variables in alphabetical order. So what would we do with this one? Okay, 9 times 2 is 18. X to the 10th, y to the 14th. Good. We treat each variable separately. Y to the 7th, or x to the 7th and x to the 3rd. 7 plus 3 is 10. We get x to the 10th. Y to the 5th and y to the 9. We get y to the 14th. When we divide, follow the same pattern. We divide the counts. What's 8 divided by 4? 2. Now, x to the 5th divided by x to the 3rd. If you think of that again, x to the 5th is 5 x's multiplied together. X to the 3rd is 3 x's multiplied together. We cancel out. We're left with 2 of them. X squared as a result. The shortcut, of course, is just to subtract. 5 minus 3 is 2. So what are we going to get here? 36 divided by 9 is 4. X to the 5th, okay. Y to the 1 or just y? How about something like this? We'll divide. 42 divided by 7 is 6. Okay, 5 minus 8 is negative 3. So a to the negative 3rd, good. B to the 2nd, and c to the negative 4, good. This is c to the 1 if there's no power there. 1 minus 5 is negative 4. Now, what does that mean to have a negative power? A couple ways to look at that. If I had x squared over x to the 5th, if I were to divide that out and subtract 2 minus 5, I would get x to the negative 3, wouldn't I? But if we look at it using our brute force method of writing it out and canceling, we would cancel out x and x, and we get 1 over x to the 3rd. Remember from last semester that negative power, x to the negative 3rd, is a reciprocal. That means 1 over x to the positive 3rd. We looked at this with our numbers. Say we have 5. 5 to the 3rd power is 125. What's 5 to the 2nd power? 25. 5 to the 1st power is 5. What's anything to the power of 0? 0. Careful. If you remember our pattern here, every time we reduce the power by 1, our answer gets divided by 5, because 5 is the base of our power, our exponent. If I divide by 5 here again, what do I get? 1. Anything to the power of 0 is 1. Now, I warned you about this. At some point on a quiz, you may see me do something like this. What's that equal? 1, because it's all to the power of 0. Anything to the power of 0 has to be 1. So as we keep going here, 5 to the negative 1, our power was reduced by 1 again. The answer has to be divided by 5 again. So that becomes 1/5. 5 to the negative 2, 1/25. Notice, as we pointed out last semester again, the connection between 5 to the second and 5 to the negative 2, they're reciprocals. 5 to the second power is 25. 5 to the negative 2 power is 1/25. So back up to this here. This is just fine written like that with the negative powers. I would accept that. I have no problem with it. However, in most textbooks, you would see the answer, because they don't like negative exponents. In most textbooks, you'd see the answer written like this. They took the a to the negative 3 and the c to the negative 4, and they put them on the bottom of the fraction. They made them reciprocals in order to get rid of the negatives and the powers. You guys remember what the fractional power means? How about this? If you have your calculator with, punch in that 9 to the power of 1/2 and tell me what you get. Three. Okay. How about this? 16 to the power of 1/2 and tell me what you get. Get 4. 25 to the power of 1/2. 5. 49 to the 1/2, you can guess is 7. Somebody said it over there. Was it Jared? That power of 1/2 is the same as the square root. Now, we talked briefly last semester about how the fact that there's actually 2 answers to the square root. Square root of 9 is actually 3 or a negative 3. Your calculator just doesn't recognize that negative answer. The power of 1/2 and the square root are actually defined to be the same thing. Where does that half come from? Well, remember, the square root is really the index of 2 on that radical symbol. We don't write it because it's just implied. The square root's so common, we save the ink and we don't put that 2 in there. But if you recall, there were other roots. We could have a third root, which is asking us, if I put in the third root of 27, what that's asking us is what number to the power of 3 would equal 27? Well, shoot. First day of class, I knew I was going to forget to silence my phone. The other way we could write this is, instead of the third root of 27, 27 to the power of 1/3. If you punch that in your calculator, what do you get? You get 3. 1/3 and the third root are the power of 1/3 and the third root are the same thing. So how about, oops, don't want the root. 64 to the power of 1/3. What do we get? Not everybody at once. 4. So back to this 8 to the power of, I don't know where that 8 is. 8 to the power of 2/3. Now remember, powers can be split up. If I have 2 to the power of 12, I can split that up into 2 to the 10th times 2 to the 2nd. Because when I'm multiplying numbers that have the same base and have the powers, I'm going to add those. 10 plus 2 makes 12. Make sense? Over here, I can do the same thing. 8 to the 2/3 can be 8 to the 1/3. Actually, I don't want to do it that way. Sorry, I'm still getting going for the semester too. The way I really wanted to break this up was this. 2 to the power of 4 to the third. Because what do I do with those powers there? When you have a power of a power, you multiply. 4 times 3 is 12. And that's what I really want to do over here to break it up. 8 to the 1/3 to the power of 2, because 1/3 times 2 would give me 2/3. What's 8 to the power of 1/3? Well, what's the third root of 8? 2. To the power of 2 would be 4. So I might have 16 to the power of 3/4. Well, I would split that up. 16 to the power of 1/4, and then to the third. What's the fourth root of 16? 2. 2 to the third is 8. Make sense? Let's go back and explore this little rule here that I kind of quickly skipped over. When we have the power of a power, x to the 5th to the power of 3, of course, what is that going to come out to be? X to the 15th. We multiply those powers because this is x to the 5th times itself. There's 3 of them multiplied together. 5 plus 5 plus 5 is 15. What if we have numbers involved in there? Like this. Well, we have to take the number, the count, has to go to the 6th power. What is 5 to the 6th power? 625, right? 15,625. X to the 7th to the power of 6? 7 times 6 is 42, good. And y to the 48. There it is. Any questions? So the big thing that we kind of the peak of our algebra last semester. I'm not going to get back into systems of equations today, but we will use that a little bit throughout this semester. I can see the grins out there of agony. We'll review it when we get to it. Don't worry. Where we kind of ended up the step below systems of equations with stuff that looked like this.
Completely unrelated matter. What kind of car are you driving again?
So anyway,
and will it drive tomorrow?
Remember, when we look at these, we have to ask ourselves, how was this equation built? How was it put together? Remember, we always start out with just the variable. And our order of operations tells us how it was put together. We find the equal sign right there, and we look at what is on the same side of the equal sign as the variable. We have the 3 and the 7. Then we ask what operation was used to attach this number to the variable. The 3 was multiplied and the 7 was added. Order of operations says which one happens first. We multiply first. So when this equation was built, x was multiplied by 3, and then 7 was added to it. Now, we also talked about this last semester. When we put something together, whether you're putting a machine together or assembling a product you bought at the store, if something goes wrong and you take it back apart, what's going to be the first piece that comes off? The last piece that went on. So the last piece that was put on this equation when it was built was adding 7. When we take it apart, that's the first piece that has to come off. How to remove a plus 7? Subtract 7. So it's gone there. But we also discussed the idea that these equations are balanced scales. If I subtract 7 from one side, it's going to make the scale go out of balance. So to keep it balanced, I have to subtract 7 from the other side. So over here, the plus 7 is gone. That's what we took off. On the other side, we subtract 7 from the 22 to get 15. Now what do we have to do? Divide by 3. So x equals 5. Tell me what to do here. Add 3, very good. Making sure we add 3 to the other side of the equal sign as well. 46 and 3 make 49 equals 7y. And then we do just divide by 7. So 7 equals y. Now, if we get to this point and we're not sure if we did it right, what can we do? Yeah, we say 7 equals y or y equals 7. That means we should be able to replace this y with the number 7. So instead of 46 equals 7y, we should do 46 equals 7 times 7 minus 3. 7 times 7 is 49, minus 3 is 46. So we do have the same value on both sides of the equal sign. There we are. What do you think? Good stuff? What do we do here? We have to get rid of one of the variables because there's a variable, the same variable appears on both sides. We usually get rid of the smaller one, which will be the 3x. So subtract 3x. Leaves us with 43 here. But to keep it balanced, we need to subtract 3x from the other side. Can we take it away from the negative 7? No. We can only take it away from other x's. So 8x minus 3x is 5x. Now, add 7, good. So 5x equals 50, and then divide by 5. X equals 10. And just like before, we can replace x with 10 now and make sure this works out. 8 times 10 is 80, minus 7 would be 73. 3 times 10 is 30, plus 43 would be 73. You get the same value on both sides. This one's for you, Jared. N times, well, n d pi over 12. This is actually one of your cutting speed formulas, your surface cutting speed formulas. If I tell you that n equals 800 and d equals 1/2, we can evaluate this formula. In other words, we can find out what s over here equals when we plug all those numbers in. All you do, if we recall, is take the n and replace it with 800. D gets replaced with 1/2. Of course, pi is just pi. It's 3.14 is what we normally use. Divided by 12. So what do we have to do first? Well, remember, when we have this here, that fraction bar tells us we have to do everything on top first, then everything on bottom, then we're going to divide. So on top, we're going to do 800 times 1/2, which is 400 times 3.14, which is 1256. Now on bottom, there's nothing to do. There's just the 12. So we're going to divide to get 104.666, 104.67. That would be feet per second, would be your surface cutting speed at the tool. That depends on the material.
Yeah.
Aluminum, that's not bad. Yeah. Actually, aluminum, they'll say up to 250 feet per second, but problem with that is you have to have a pressurized coolant, otherwise it just gums up your tool. Okay, well, I think for your first day back from break, that's probably enough suffering. No homework today. Don't get used to it. You guys know me well enough to know that doesn't happen very often, and you will pay for it later. Have a good one. We'll see you tomorrow.